data and you want to cluster them by subject. So since clustering is NP hard for many of the objectives that you care about, you have a lot of approximation and heuristic algorithms. And one large class that we focus on is the class of agglomerative techniques, which take the data and which arrange them into a cluster of trees and then prune the tree to get the cluster. Okay, I'll describe this in more detail later during the talk. But the point here is that there are so many ways in which you could build this tree and then prune it, and which is the best, and there is no one technique that is going to work the best in all the applications. So our goal is to choose the best algorithm, the best merging and pruning technique for a given application domain. And another problem that we focus, another class of algorithms is that we focus here is a class of algorithms for integer quadratic programming, where your goal is to assign plus 1 or minus 1 values to decision variables in order to maximize a quadratic objective. And this is an abstract problem with many diverse applications. We focus on MaxCut in this talk, but our analysis holds good for many other general integer quadratic programs. So since this is also a hard problem to solve, a very popular way of solving this is by relaxing this integer quadratic program to a semi-definite program. By relaxing, I mean that instead of finding plus or minus 1 values for these decision variables, you find vector assignments to these decision variables. I'll describe this in detail later. But once you find these vector assignments, you need to round them back to integer assignments. And there are many interesting ways in which you could round them. And you want to know which is the best way of rounding them back for a given application. Sure.
What's the minimal cut and maximum cut difference?
Oh, so in MaxCut you want to partition the vertices such that you maximize the total edge weight that is cut. That is a hard problem, but it's not the same as min-cut. So I'll describe the problem in more detail in the talk. Yeah, please feel free to stop me if you have any questions or if you can't hear me. So a little bit of background work. Application-specific algorithm selection has had a long history of research in AI and empirical research under different related names, and it has led to breakthroughs in many different fields. Until recently, this has been mostly this has had only empirical research, but recently there was this learning-theoretic model that was proposed by Gupta and Roughgarden, which is a very general model that applies to the kind of algorithms that we consider in this talk. And they proposed and studied this model for very simple algorithms like knapsack and greedy algorithms. We consider classes of algorithms which have randomization in them and which have more complex multi-stage procedures. So first I'm going to define our algorithm selection model more formally in terms of, more formally, and then we'll see how it is related to learning theory. And then I'll go through a little bit of learning theory background in order to help you understand the results. And then we'll go to the main results. Okay. So now I'll make my problem definition more clear. So I said you're given, there's this universe of all problem instances, and the application defines an unknown distribution over these problem instances. So basically it says which problem instances are more common to my application. And given this unknown application-specific distribution, I now have a family of algorithms, which could be a possibly infinite family of algorithms, in order to solve the problems in this application domain. And your aim here is to pick the best algorithm for the application. So in order to define what is best, I should develop a notion of cost, where the cost function is applied on maps an algorithm and a problem instance to some real value. So throughout the rest of this talk, I'll use the gear symbols to refer to an algorithm and I to refer to a problem instance. So basically the cost function runs the algorithm on a problem instance and it outputs a value. Okay, so what is my ideal goal here? I want to pick an algorithm from A, the family of algorithms that I care about, and this algorithm should have the best performance in expectation. What do I mean by expectation? If I were to pick a random problem instance from this application, I want the cost of running this algorithm on that application to be smaller than any other algorithm in expectation. But an obstacle here is that I do not know the distribution over problem instances. So this goal is too ideal for me. So the best I can hope to do is sample some typical problem instances. So I sample some problem instances to get an idea of what the distribution looks like. And I scan the algorithms and I pick the one that performs the best on those samples. So I pick an algorithm from A that is empirically best. So that's the word I'll use, empirically best. And the question here is this: how do we use these sampled problem instances to find the algorithm from A that nearly minimizes the expected cost on a future instance? So I say nearly here because now I'm doing something approximate. I'm not really looking at the distribution, but I'm only looking at samples. So I can't hope to find the optimal algorithm on the distribution. So let me go through this a little more slowly, and I'll pose two questions here, which we'll try to answer in the rest of the talk. So I have a family of algorithms, and I have a cost function that maps algorithms and problem instances to real values. And I have this unknown distribution over problem instances, which I can't really see. So I can only sample some problem instances from this distribution. And then I'm going to pick the empirically best algorithm from A on these samples. And I hope that this algorithm is also near optimal in expectation over the distribution of algorithms. Okay, so this is my protocol, and I want to pose two questions over here. So the first question is, how do I ensure that the algorithm that I picked, the empirically best algorithm that I just picked, is also near optimal in expectation? Okay, to understand this question, let's pause and think about this for a while. If I were to sample a single problem instance from the distribution, it could be a stray example, and an algorithm that runs really well on the distribution may run very badly on the distribution. So an algorithm that runs very well on the sample may run very poorly on the distribution. So on the other hand, if I were to draw millions of problem instances from the distribution, I now have a better idea of what the distribution looks like, and I could then hope that the performance of the algorithm over these samples is representative of its performance over the distribution. So this idea I'm going to call as generalization, and which is something very fundamental to learning theory, where I want to generalize something about a set of samples back to the whole distribution, which is unknown. Okay. So more precisely, we will see how this sample complexity is linked to the family of algorithms and the cost function. In fact, it's linked to how complex these two things are, and learning theory will help us define a notion of complexity for these two objects, and then it will help us link it to the sample complexity. So now we have another question here, which is how do we efficiently find the empirically best algorithm from A? So if we have established that we don't really need too many samples to do this generalization, how do we efficiently find the empirically best algorithm using these samples? Does anyone, if anyone has any questions, again, feel free to stop me. Okay, so now that I'm done with the model, let me get to a very basic learning theory model, and we'll see later how this well reflects our algorithm selection problem. So typically in learning theory, you are given an input-output domain, such as the space of all emails, which are my inputs, and two labels, which are my outputs. So in nature, there's a distribution over these input-output pairs. So nature tells me which kind of emails are spam and which kind of emails are likely to be not spam. Okay. Given that, I as a learner have a set of proposed mappings between the emails and the labels. So these are the functions f1 that map email to labels. And I need to pick the best function. What do I mean by the best? So I define a notion of cost, which takes as input a proposed mapping and checks whether that mapping predicts the label on a given input-output pair. And in order to pick the best function, what I would do is, since this distribution is unknown, I would pick some typical email label pairs, and I will look at all my proposed mappings between emails and labels, and I'll pick what is empirically the best. And the question here that I would ask is, how do I use these sampled email label pairs to find the function from f that nearly minimizes the expected cost on a future instance? Which means this function basically reflects this input-output mapping on the samples. I hope that it also reflects the input-output mapping over the distribution. The distribution over the input-output mappings. Okay. So you can see that this somewhat looks like the slide of the algorithm selection model, and we'll see in a couple of slides how this exactly reflects our own problem. But before that, let me try to answer this question using learning-theoretic. Using learning theory. So let's focus on this question. So recall, in summary, what I want is that if a function is very good on the samples, I hope that it's near optimal on the distribution. So in order to ensure this, let me ensure something a little stronger, which I will call as generalization, which is a word I introduced a couple of slides back. So more formally, what generalization means is that for each function in my class of functions or my class of mappings, its empirical performance over the sampled email label instances, that is how well it predicts the labels on those emails, must be representative of its expected performance over the distribution of all email label instances. So this is generalization, and I hope you're intuitively convinced that if this were to be true, then that would be true, because my samples are now representative of the distribution. So let me make this a little more formal by introducing an epsilon parameter, which is used to quantify how much of generalization is happening. So if this were to be true, then this is true. My near optimality can also be quantified in terms of epsilon. So for now, let me forget that part. Let's just focus on this question, and let's see how learning theory answers this. So recall that in order for generalization to happen, I want more samples, and in order to answer this question, I need to know how many samples do I need to achieve this this generalization for each function. In order to answer this question, let me rephrase it a little bit. If you look at it, for each function, I essentially want generalization for the cost instantiated on that function. So let me rephrase this. So for cost instantiated on each fi from f, I want some generalization to occur. Okay? So I want to ensure something about it. So what learning theory tells me is that this sample complexity is in fact tied to the complexity of this class of functions. I haven't defined what I mean by a complexity of a class of functions, which I'll get to in the next slide, but this is what learning theory tells me. So if I define the set of all functions, so this cost, which is nothing but the cost instantiated for each input-output mapping, and if I have this notion of complexity for that class, so let me call the class cost sub f for the sake of convenience. What learning theory tells me is that the sample complexity needed for generalization over here is in fact tied to the intrinsic complexity of this object, which is an interplay between the cost function and a set of all mappings that I'm working with. Okay, so let me define what I mean by the complexity of cost sub f. So in order to define this, okay, this is a standard definition in learning theory, which is pretty natural. So in order to define this, let me work with a more general function class G, and I'm going to ask how rich is this function class, and this is beautifully encapsulated by the idea of VC dimension. Okay, VC dimension is a notion of complexity for binary valued classes, but we are interested in real valued classes because cost sub f is a set of real valued functions. So this can be extended to real valued functions, but I will not go through that during this talk. Okay. So what VC dimension is basically, it is the size of the largest sample set S that can be labeled in every possible way by the functions in class G. Okay, let me go through this a little slowly using an example. So let's say I have this set of all threshold functions which map the real values to 0 or 1. So there is this threshold for each function, and anything to the left of the threshold is 0, and anything to the right of that threshold is 1. So this is an infinite class of functions. Now if I were to pick a single sample, I could label it in both possible ways using some 2 functions in this class. But if I were to pick 2 samples, I would not be able to label the left point as 1 and the right point as 0 by any function in this class. So there is this inherent limitation in this seemingly infinite class of functions. And that is well encapsulated by VC dimension as a single number. And this idea can be extended to pseudo dimension for real valued classes. And you don't really need to internalize this idea, but for the rest of this talk, I'm going to talk about pseudo dimension for various algorithms. And okay, let me get to that in the next slide. Okay, so why were we looking at all of this? We had this generalization guarantee that we wanted in the learning theory problem, and we said that the sample complexity is proportional to the intrinsic complexity of cos sub f. So in fact, the answer is, if I had so many samples, if I had like pseudo dimension of cos sub f many samples, then I'm guaranteed that this generalization is going to hold good. So this is a standard result in learning theory, and we'll see how this will be useful for our own algorithm selection model. Yeah. Sure.
Is there, just because you know this many samples are required, is it efficient to actually find the function when that function after I've had some samples? Like, does this theorem guarantee you that, or is it only guarantee that there is some given function?
So okay, so there are lower bounds too. So I should make sure that I at least have so many samples, but then I know that if I have so many samples, I'm guaranteed to find a near optimal function.
No, I'm saying if you find it efficiently, is my question.
Oh no, it's not clear. It's not clear why it's efficient. Yeah, okay.
Yeah.
It's not clear why it's efficient. We'll see that in the rest of the talk. Yeah, good. Okay. So let's see how. Okay, so now I'm going to show you how the learning theory model parallels our algorithm selection problem. So recall that I have this input-output domain of email label pairs. So instead, in our case, we have this set of all problem instances. And recall that we had a set of functions, and we have to pick the best function. Now we have a set of algorithms, and you want to pick the best algorithm. And you have an appropriate cost notion, which maps algorithms and problem instances to real values. And you picked problem instances, and you found the empirically best problem. And the question was again identical. How do I use the sample instances to find the algorithm from A that nearly minimizes the expected cost on a future instance? So here the notion of cost is different from what it was in the context of learning theory, but then the results from learning theory can be applied here. So how exactly? Okay. So I can pose a very similar generalization question. So how do I ensure that for each algorithm in my class of algorithms, this empirical performance of that algorithm over the sampled problem instances is representative of its expected performance over this distribution? So if I were to answer this question, in a similar manner, I can define something called as cost sub A, which is the cost function instantiated for each algorithm. And so basically this is an interplay between the cost and the set of all algorithms. So I can answer similarly that the sample complexity is in fact proportional to the pseudo dimension of cost sub A. So I can get this upper bound on the sample complexity. So now that I have answered this question, okay, why did we go through all this trouble? Just to recall, we wanted near optimality of the empirically best algorithm. Okay, so now I'm going to use this result for the rest of my talk, and we'll also see how you can find the best algorithm, empirically best algorithm more efficiently. So this brings us to my results on clustering. So please let me know if you have any questions at this point. Okay, cool. So let's get to clustering. let me define clustering more formally. So you have a set of n points and the pairwise distances between them, and you want to partition, any clustering algorithm is going to partition that into set of into k sets, okay? And you want to minimize the cost. For example, this could be the maximum radius of the clusters or the average radius of the clusters. This corresponds to things like k means, k medians, k center, okay? And in the rest of this talk, I'm going to consider an arbitrary cost, because our results generalize to any of these popular notions of cost. Okay, so now clustering is an NP-hard problem for these notions, for these objectives. So you have a rich class of approximation algorithms, and the one that I'm going to focus on today is a class of algorithms, each of which consists of 2 steps. So in the first step, you're going to build a cluster tree, and the second step, you're going to prune it. So what exactly do I mean by that? I'm going to take all the data points that I'm given in a particular problem instance, and I'm going to merge them iteratively into clusters. So in each step, I have this set of clusters, and I want to merge 2 closest clusters. So I haven't defined what I mean by closeness of 2 clusters. We'll get to that in the next slide. So I'm going to merge them one after the other until I merge all of them together. So now, in order to get a pruning, I use some objective and I prune it, and I get the best pruning to get a k clustering. Okay, so where does the richness lie in this class of algorithms? So this is the general outline. So the richness lies in the definition of closeness, which I really didn't tell you yet. So recall that I have these clusters which I want to merge, and I'm going to define a notion of closeness between clusters. So for one example notion is called as average linkage, where I look at the average pairwise distance between points in the cluster. So another popular notion is single linkage, where I look at the shortest pairwise distance, and another is complete linkage, where I look at the largest pairwise distance. So these are popular notions, and these algorithms have really good guarantees under worst case in various settings. So we choose to work with this. In fact, we work with an interpolation between all of these, which gives rise to an infinite class of algorithms for this talk. So I'm going to define what I mean by alpha linkage exactly, which is an interpolation between all of these. First, I'll define a simple notion of alpha linkage. So recall that I want to, this is what alpha linkage is basically a distance between two clusters, and based on which I'm going to build the merge tree, build the cluster tree. So here, this simple notion is a linear weighted sum of the smallest and the largest pairwise distance between those 2 clusters. So you can see that this interpolates between complete linkage and single linkage. Okay. So we'll develop a richer notion later in the talk, and that also goes through average linkage. So let's analyze this for now. So what is our goal? Let's recall. We have a set of algorithms and some cost function, which now boils down to picking an alpha. So the class of algorithms is now parametrized by alpha. So I want to pick the best alpha from that family, given some sampled clustering problem instances. So there are 2 questions here which I wanted to answer. How many problem instances should we sample for near optimality? And how do we efficiently find the empirically best algorithm? So this requires that I also look at what the pseudo dimension of cost sub A is. Okay. So in order to understand this, okay, what exactly do I need to know? I have a set of samples, and I have this range of parameter values alpha. I need to vary alpha along this and see how the empirical average cost varies and pick the best alpha. So this potentially might involve having to run infinitely many algorithms on a set of problem instances. So this brings us to the key challenge here, which is that 2 adjacent values of alpha may potentially lead to very different cluster trees. So recall that alpha determines how I build the cluster tree in the first step. So this is an iterative process, and even if one step is going to change because I changed alpha, the rest of these steps could change in an unintuitive fashion. So it's very difficult for me to wrap my analysis over that. And as a result of these different cluster trees, I'll get different prunings and hence completely different costs, which I have no clue how it's going to be. So to understand this a little better, let's look at standard learning theory problems where instead of a parametrized algorithm class, I would have a parametrized function class. And as I change this parameter value, for example, the slope of this line, a smooth change over here is going to reflect as a smooth change in the function space. I know logically how this is going to, the function is going to change, and hence I can understand how the cost is going to change. But in our case, I don't really know how the cost is exactly going to change. And we see, and we show how you can, in fact, address this. So we have this cool result where we pick the alpha line, and we show that you can, in fact, divide this line into a small number of intervals. More precisely, the number of intervals is proportional to the number of samples that I've picked and the size of each problem. So there are endpoints in each problem. So what is cool about these intervals? If I were to pick a specific alpha from, if I'm going to change the values of change alpha within a particular interval, it's going to result in the same set of trees. Which means, so the trees that I get on different problem instances might be will of course be different, but as I vary alpha over this interval, this set of trees are not going to change. But recall that if I were to jump to an adjacent interval, I have really no clue how this set of trees is going to change, but within that interval is going to be the same set of trees. So what we essentially prove is that as we sweep through the values of alpha, there are going to be very few points at which the algorithm is effectively going to change in its behavior over a fixed set of sample instances. And so as a result, we get the same set of pruned solutions and hence the same set of cost, which means I have the same empirical average cost within each interval. So if I were to draw the empirical average cost of these algorithms of each alpha over S, I'm going to get this piecewise constant function where the number of pieces is pretty small. So what exactly does this give us? Okay, let's just remember this. Sure.
Where does the instance come from?
From the distribution.
You distribute.
So I have. So I'm working in an application domain, and there's this distribution over problem instances, and I have the ability to draw problem instances from that domain. So that's the model I'm working in. Does that answer your question?
Yeah, but I saw what you're talking about is you given the instance already.
Oh, this is for any arbitrary set of problem instances. So you have drawn S from the distribution. It could be any arbitrary set of problem instances, and this is going to hold good.
So the summary is actually very different. Your sum here is ID distribution for each?
Yeah, we assume IID.
Okay.
It's drawn from the same distribution but independently. So that's the model that we work in.
Yeah, but in classification, why don't you assume the conditional independence given the labels? It's another kind of sampling.
Yeah, I mean that's a relatively, I mean that's not what we do here in this. Okay, so going back to what this.
And so you try different alpha, you have the same subset of instance.
Yes, so as we try different alpha within the, we try all these alpha on the same set of instances, and we want to know how the cost varies. Okay. Thanks for clarifying. So what this gives us is first a pseudo dimension bound where we show that the pseudo dimension of cost sub A. Recall that cost sub A is a set of functions where the cost has been instantiated for each algorithm. The pseudo dimension of this is upper bounded by log n because of this cool property, which automatically gives us a sample complexity upper bound. We also show a lower bound, which is a technically more intricate analysis where recall that in the definition of VC dimension, I had to the definition relies upon having a set of instances which can be labeled in every possible way. So we actually have to come up with clustering instances which can be labeled in every possible way by cost sub A. So, okay, now that I don't need too many samples, can I have an efficient algorithm selection procedure? So all that we need to do now is we show how we can solve for the intervals, and then we run the algorithm for only one alpha per interval. So instead of having to run alpha for every run the algorithm for every alpha, since the empirical average cost for a given set of instances is going to be the same within each interval, I only need to pick some alpha from each interval once I found the intervals. And then I can run alpha and find the empirical average cost, and I can find the empirically best interval. So this is going to be efficient because the number of samples is not too large, and I have a very few intervals. Okay. So going back to our question here, where we have sample complexity is now very small, where n is the number of points in each problem instance. Sure.
Sorry, did you say how efficiently can you calculate each of the intervals?
Yeah, you can efficiently calculate. So it's basic. You only need to understand where your decisions are going to change. You recall the whole distance notion that I had between clusters. I need to solve some a set of linear equations and find these alphas.
Okay.
So you can efficiently find it. It's in polynomial. So yeah. Okay. We also have more general results. So as I said, we had the simple notion of alpha linkage in the first. So recall that in the first step of my agglomerative clustering techniques, I wanted to merge the points into clusters, and I had to define notion of clusters in order to choose the two closest clusters to merge. So instead of this linear definition, we consider a much richer non-linear definition, and for alpha equals 1, it also interplays through average linkage, because this definition considers every pairwise distance between the pair of clusters. And we show that the pseudo dimension for this class is theta of n, and it's not theta of log n, which is something that you expect because it's a much richer class of algorithms. And another set of results, okay, we recall that it's the first step that had the richness in our class of algorithms. We also consider performing the pruning using different dynamic programming objectives. Okay, so why exactly does that make sense? So if I were given a k-means or k-median objective in order to evaluate my solution, I really need not consider different dynamic programming objectives. I could just use that objective, and okay. So, but then if you were given ground truth clusterings, and your aim is that the solution provided by the algorithm must look as close as possible to these ground truth clusterings, you cannot really use the information about the ground truth clustering in your dynamic programming, because that will be cheating. So all you can hope to do is use some standard objectives like k-means or k-medians in place of that, and then evaluate your solution according to its distance from the ground truth clustering. So now this is a much richer class with two different parameters, and we also show how you can analyze this class. Okay, so now this brings to our discussion on MaxCut. So in the MaxCut problem, so let me define the problem more formally. So you have a graph G of n vertices, and there are edge weights between these vertices. And any MaxCut algorithm is going to partition these vertices into two sets, and you evaluate how this algorithm, the solution of this algorithm, using an objective function which you want to maximize. So what exactly you want to maximize is the total edge weights connecting these two sets. Okay, I'm going to use the term objective instead of cost. It's just a small thing because I want to maximize it and not minimize it. So it's essentially the same as cost that we discussed in the previous part of the talk. So since this problem is hard, you have a lot of so you have this popular approximation technique. So I'm going to give you an outline of that. So what you would do is you would formulate this as an equivalent integer quadratic program, which is also going to be hard to solve. And then you relax it into a semi-definite programming. I will describe this in my next slide. The semi-definite programming relaxation is not going to give you an integer assignment to the variables. So you have to transform the STP output into a graph, graph cut. And there are potentially many different ways in which you could do this transformation. And the question here is, which path through this flowchart is the best for a given application? And so in order to answer this question, let's look at the algorithm, the first two steps a little more clearly. Let's say I am given, okay, so this is the integer quadratic program. So for each vertex, I have vi, a decision variable, which has to be assigned as +1 or -1. And I have to do this keeping in mind an objective. So what is this objective? So given this, so if I were to assign vi's as +1 and -1, it automatically defines a cut over the edges. And that can be expressed as a quadratic objective over there. But this is hard to solve, so you have a semi-definite program relaxation. So what you do is, instead of finding integer values, you're going to find an embedding of the vertices on a unit sphere. So you're going to find these vector solutions to a slightly different objective. So instead of vi's, you're finding these xi's, and what you want to maximize is not that. So there you had vi, vj as your quadratic term. Here you have a dot product of xi, xj. Now, your semi-definite programming can yield an optimal embedding. You can find the optimal solution for these xi's in the semi-definite program. But the question that I'm still yet to answer is, how do I assign labels to the vertices based on their embedding? So each vertex now has an embedding on this unit sphere, and you need to transform that back into a graph cut, which means into integer assignments. And there are many different ways. So we are going to look at one algorithm now. So it was proposed by Gomans-Williamson. So recall that I have this embedding of the vertices on a unit sphere, this optimal embedding for the SDP. And I choose a random hyperplane. This is a simple technique. I simply choose a random hyperplane, and then I partition the vertices based on that. Okay. This is a very simple algorithm. So this is a randomized algorithm. So it's known that this produces a 0.78 approximation in the worst case. It's an expectation over these random draws of hyperplanes. So this is just a single algorithm. So I've been talking about a family of algorithms. So let me get to that now. So just to describe the family of algorithms, let's note that this is a deterministic rounding approach. So once I fix the hyperplane, I have a deterministic approach to defining which side of the cut these vertices belong to. Okay. So the family of approach SDP transformation techniques comes from the fact that I can use a randomized rounding approach, where instead of assigning a hard cut to these vertices based on the random hyperplane that I just picked, I could rather assign a probability over the two labels for each vertex based on how far away it is from the hyperplane. So intuitively, if a vertex is very far away from the hyperplane, I would assign a probability distribution that's skewed towards one of the labels. And if it's very close to the hyperplane, I would assign a probability distribution that's pretty uniform to both the labels, because I don't really know which side of the cut it belongs to. But in order to do this, I need a rounding function. So what is a rounding function? It maps distances from the hyperplane to probability values. And I get these probability values. Okay. So here so now this is not really going to give you a proper cut of these vertices, but I'm going to define obj, which is how I'm going to evaluate the solution. I'm going to define obj to be the value of these cuts in expectation over the random hyperplane draws and over this probability distribution. I'm not going to get into further details here, but the idea is that obj is not for proper cut over the vertices, but for this fractional cut over the vertices and over the random hyperplane cross. Okay, so now I said there is this rounding function, and I could potentially use different rounding functions, and that's where the family of algorithms comes from. So here in particular, we are talking about an S-linear rounding function, in which you have these piecewise linear functions, and S is a parameter that determines the slope of the middle piece. So I want to know which is the best S linear rounding function that I can use for an application. And Feige proposed this family of algorithms, and he said that there's some rounding function from this algorithm that performs much better than what Gomans-Williamson proposed, which was what we saw in the previous slide. And he didn't show how to find it efficiently, and we show how to find it efficiently given an application. So recall, now going back to our two questions, we effectively want to find the best S given the objective, and that means so effectively I want to answer how many problem instances should we sample so that the S that I pick over a set of problem instances is near optimal, and how do we efficiently find the empirically best algorithm from A using those samples. So recall that means I need to understand the pseudo dimension of obj sub A, where obj sub A is this interplay between the objective and the class of all algorithms that I have, which are based on S linear rounding functions. Okay, so similarly, what do we need to do here? As I vary S over the values of all possible S, I want to understand the empirical average objective on the set of sampled instances.
Is that the rounding parameter you were talking about a minute ago?
Yeah. S is what determines the rounding function that I use.
But notice this doesn't use anything from the problem itself. You're just using the projection onto the sphere, and then you're choosing a random hyperplane, and then you're still flipping more coins to decide which are the close ones. Why can't you use an algorithm like pick ones that would improve your solution to go around one way or the other, like a greedy algorithm? Just pick it and say, well, I'm going to round it to that side because it's going to work better if we do that.
So these are a class of algorithms that are known to work pretty well, and here we do use information about the problem instance, but so where you have this STP.
Solve the some indefinite or whatever program to do that.
Yeah, so that makes use of the problem instance, but the value S is something that you have to figure out. But yeah, I can see you can potentially use other techniques, but we haven't focused on that in this talk.
So you sample your instance from the
unknown
from the SDN programming, semi-definite programming results.
Okay, these sampled problem instances are MaxCut problems, and you apply SDP on them, and you get this embedding, using which you can define the objective value. So for each sampled MaxCut problem instance, there is an SDP embedding, a fixed SDP embedding that can.
But actually, it's very hard to sample from a graph because the graph, the instance, is not independent.
No, okay, so I'm not sampling vertices of a graph. I'm sampling a whole graph instance. So there's this distribution over different MaxCut problems. I'm sampling a MaxCut problem as a whole. So the distribution over problems are not vertices. Similarly, in the case of clustering, the distribution is over clustering instances and not the individual data points themselves.
Okay. Can I take the example that you have a Facebook network and Twitter network and other networks, and you sample one of the networks as a whole.
Yeah.
You did not sample a subgraph of the Facebook network.
No. So yeah. Okay. So in order to find the best S, empirical S, I would potentially have to run the algorithm for each value of S. But here is another problem. The algorithm is randomized, which means I will have to sample every random hyperplane and average my cost over these hyperplanes. Okay, so that's an obstacle which we have to cross. So in order to cross this, we note that if we were to fix the hyperplane, there is an easy way of understanding how the cost varies with S. Okay, but the problem is when you have to average this over all hyperplanes. And let's see this a little more closely. So ideally, we want to analyze how the objective over a set of samples varies with S. And we want to analyze the pseudo dimension of obj sub A, where obj sub A is this set of all objective functions instantiated for each S. But this is hard to analyze. Why? Because each of these is an expectation over a random draw of the hyperplane. Okay? And this is sort of difficult to analyze. So what we propose in our work is let us analyze this inner objective. Okay. So I'm going to analyze this. What I mean by that, for each problem instance, instead of understanding how the cost varies over the random draws of in expectation over the random draws of hyperplane, I'm going to fix a hyperplane for each problem instance. And I'm going to see how the cost is going to vary only for that fixed hyperplane. Okay. So it's not immediately clear why that would be good, but we show that we can as well do that. So in order to analyze this, I need to analyze the pseudo dimension of this new objective, obj sub A, where each function in this class is now the objective instantiated for each S, and it maps a problem instance and a hyperplane to a cost value. So the one above is simply this, but in expectation over all the hyperplanes. Okay. So we overcome the randomization in the algorithm through this. Yeah, sure.
So do you still have like a nice locality property with S where like you don't have to try out all of the infinite values of S?
Yeah, we do not have to.
Okay.
Yeah. So we show that in the next slide.
Sorry.
So yeah, so this is what we originally began with, but we show that we could equivalently do this. So let's look at the objective value. So I have this new function, which now also takes in as input the hyperplane. And instead of sampling just MaxCut problem instances, I'm going to sample random hyperplanes for each problem instance. I'm going to sample a single random hyperplane for each problem instance. And I'm going to find this S, the best S for this new objective. It's not the same as the previous S, but we show that you end up finding a very good S. So instead, now you need to understand this new pseudo dimension. Okay, we show that these two questions of how many problem instances do we need to sample for near optimality, and how do we efficiently find empirically best algorithm from A, can be answered by finding the best S parameter for this new objective function. So now we need to do this process for this new objective. So again, we still haven't really answered whether I need to run the algorithm for each value of S. And we show that we don't need to do it. So given a set S of problem instances and a fixed hyperplane for each instance, we show that there is this cool property of the empirical average cost, which is that you can divide the S line into a small number of intervals, and the empirical cost is going to be linear or quadratic in those intervals. So, and in fact, you can derive the expression for this linear or quadratic cost by looking at the MaxCut problem instance and its embedding. So using this cool property, we similarly prove a pseudo-dimension result, which is that the pseudo-dimension of this new objective sub A is upper bounded by log n, and we also have another intricate result for the lower bound. And once we have established that you do not need too many samples, we now need to go look for the efficient algorithm selection. So what we have to do is we have to pick problem instances from the distribution, and we have to pick these random hyperplanes, and then we have to solve for the intervals, and we show how you can do that. And then we derive the actual quadratic or linear expression for each interval, after which you can find the best S in each interval. And then you can find the overall empirically best S. Okay, so I'm almost done. So we also have more general results. So recall that S defined a family of S linear functions, where S is the parameter of the slope of the middle line. We also show an identical result for families of generic sigmoid-like functions, which have a single parameter. And we have a similar pseudo-dimensional result, and we can similarly find an efficient algorithm for these. So this brings me to the summary of my talk. So we looked at two large and widely used classes of algorithms, one for clustering, which are based on agglomerative clustering techniques, and then SDP rounding techniques, which could apply to MaxCut and other problems. And we showed how efficient techniques which require few problem instance samples to learn a near optimal algorithm. So we answered the algorithm selection question in terms using learning theory. And so there are few future directions here. So we proved these lower bounds on pseudo dimension? Can we also prove lower bounds on the sample complexity? And we would also like to understand approaches like Sadzilla, which you might be familiar with, where they use machine learning to be able to select the best algorithm for a problem instance. And of course, are there other families of algorithms that are empirically used, and you want to understand how you can use learning theory to find the best algorithm from the class. So with that, I come to the end of my talk. Thanks for listening. If you have any questions, feel free to ask. Yeah, sure.
I have a question about the quantization of the alpha linkage clustering part. How can we ensure that two different alphas in the same interval will lead to the same empirical risk?
So we show that, okay, so your algorithm is based on a set of decisions that you make as to which clusters that you merge.
Right, yeah.
So we show that as there are these specific points at which some decisions flip. Okay, so in between these points, none of the decisions flip. So it's a very high level answer, but we show that it's only at the points that the decision flips that you really don't know how the algorithm is going to change. But when you have no decision flipping, so you can consider every possible pair of cluster points as clusters, and you can see at what alpha you would merge them or not. So this is a very high-level description. So
yes. So, but the single alpha will be used for all the merges.
Yeah. So an alpha. Yes, a single alpha is going to be used for all the merges. Okay. Yeah. Is there any other question? Yeah. Sure.
So it sounds like a little bit like competitive analysis. I mean, kind of stronger theorems would be that you get competitive algorithms, right?
Oh.
You know, similar to like splay trees or whatever the local specialty is, right? So you can say that you have an algorithm that as the samples change over time, that you're going to move with that and be as good as something to look into the future.
So here we do not, our model is not online in that sense. So we have this single distribution. So, and we could potentially think of how we could adapt to how the distribution changes over problem instances. So you have this. So this empirically best algorithm is pretty good for the distribution of problem instances, but we don't really know how it's going to change if the distribution is going to change. So this is not as strong as the online one.
It's future work.
Yeah. Yeah.
But the way you pseudo, like the pseudo dimension, the bound number of samples you need to say to have good, like to have basically a good generalization. This seems like pessimistic, right? That is like, that's a great goal bound. Like, did you run any experiment to see if you actually did that many samples?
Okay, that's a good question. So it is again in some sense a worst case. So pseudo dimension tells me what's the number of samples that I need in the worst case distribution over problem instances. So we haven't run experiments there, but ideally, yeah, you could think of having, using some other complexity measures like Rademacher complexity, which actually take into consideration the underlying problem distribution. But yeah, you could potentially not require so many samples at all for the generalization.
So going back to the Goldman-Williams algorithm, right? So it's the case that after you solve the semi-definite program that all the principal components are about the same? Is that right? I mean, have you looked at, because a first obvious thing would be to do a bias your sample based on the principal components, right? Then if all the points are on the north and south pole,
you would,
and of course, whatever, right?
Yes.
But maybe that doesn't work because the whole idea of the semi-definite program is to make the PCA be uniform, right? Is that right?
I guess, but okay. So we have the results that you have is for the random hyperplane. So I suppose it's likely that.
The first part. You're just solving the semi-definite program, so you get back a bunch of points on the sphere, right?
Yeah.
The naive question is, how are they distributed, right? So is it the case they're uniform? In other words, the PCA is all one?
I would think
the case that they're biased?
They would be distributed based on the weights of the edges in the graph. So I'm not sure if they would be really unbiased, because if the weights are such that all if it's a bipartite graph, for example, then I would expect that all the points on one side are mapped to one point, and all the vertices on the other side are mapped to another point. So there's no.
So has anyone looked at biasing the projection based on the PCA?
I'm not sure. I'm not sure about that. But my belief is that it wouldn't be unbiased.
But the reason it's interesting is because then you can imagine this other algorithm is interesting because it says that if they are uniform, then of course, if you take a given direction, there's going to be hardly anybody points on the north and south pole. They're all going to be around the equator, right? In high dimension, and so really, it didn't really help you very much because now all the points are in this little narrow strip.
That's true, but I don't think it's going to be uniform. So sorry, can you repeat your question?
No, the question is what is it?
Yeah.
You know, I mean, it seems like there's a fundamental question about semi-definite programming, right? Why you do that?
Is there any other question?
Let's thank the speaker again.